Okay, we're going to talk about the area moment of inertia, and this is a quantity that's actually used in mechanics of materials, and we use it to determine things like strength and deflection of a beam, okay, based on the cross-sectional area of that beam. Okay, so this is something you'll use later on. We're just going to talk about how to do it here in statics. So the definition of this is essentially given as the moment of inertia about the x-axis is simply the integral of y squared dA, where y squared is basically the distance away from the x-axis of a whole bunch of tiny little dAs, and you sum that over through, using an integral. I also have IY equal to the integral of x squared dA. Okay, so essentially, the further away the area is distributed away from the axis, the larger the area moment of inertia is. Okay, and again, this is something that we'll get into more detail in mechanics of materials. You can see where the derivation comes from. At this point, we just are going to accept this definition. Okay, keep in mind this will always be positive because I'm squaring this value, and I have an area which is going to also be a squared value. So everything will be positive here. And the units are really weird units of length raised to the fourth power. So in effect, millimeters to the fourth or inches to the fourth, which are kind of difficult units. But again, that's what they are. Okay. So another way we can define or tabulate these moments of inertia through something called the radius of gyration. Okay, and it's basically just re-quantifying the moment of inertia using the units of length. Okay, and this is used in the design of columns. Okay, in mechanics of materials again. So we'll talk more about it, when you take mechanics of materials. So the radius of gyration is essentially this value k. It's the square root of the moment of inertia divided by the area. Okay, so again, it's just another way to kind of tabulate, express how the area is distributed using units that are a little bit easier to wrap your head around. And again, that value is also used in the design of columns in structural mechanics. Okay. So again, for our purposes, all we're really wanting to do here is learn how to calculate this so that when we get to mechanics of materials, we know what it is, how to calculate it, things of that nature. So the procedure for this is similar to how we do with a centroid. We're going to draw a thin rectangle, okay? But it's very important that you draw it parallel to the axis that you're trying to find the moment of inertia about. So for this one, I'm finding the moment of inertia about the x-axis, so I would draw a horizontal rectangle with a differential thickness dy. And it's important to do that because it essentially puts all of the area at a fixed distance y away from my axis. Okay, so after I've got that parallel rectangle, again, I write the dimensions in terms of my coordinates. It's got a differential thickness dy. It's got a width of x going from 0 to here. Okay, that way I can write dA as just x dy. Once I have that, I go ahead and plug what I know about dA into whichever equation I am using based on the axis that I'm interested in. Okay, so that's how you calculate through calculus the area moment of inertia. Okay. Now, again, as with centroids, we can do this using composite bodies. Before we talk about how to do moments of inertia for composite areas, okay, we have to discuss something called the parallel axis theorem, which is basically what the moment of inertia of a body is about some axis that's parallel to an axis that passes through the centroid. So, for example, over here, if I have the x prime axis going through the centroid, and I want to find the moment of inertia about this x-axis, which is parallel to the centroidal x prime axis. Okay, so to do that, we're going to use that same definition we had before, but instead of y, okay, if I'm going from x all the way up to this dA, it's both dy plus y prime. So I have y prime plus dy squared times dA. Now, using the FOIL method, I get a y squared, a 2 dy y prime, and a dy squared. Okay, all times the dA. And I just separated that out into separate integrals here. Now, this center term right here, okay, because my x prime axis goes right through the centroid, if you remember our definition of a centroid, it was the integral of y dA over the integral of dA, right? Well, if the centroid is at y equals 0, okay, the integral y prime dA is equal to 0, so that middle term falls out, okay? This first term is the moment of inertia about the y prime axis. I'm sorry, about the x prime axis is what I meant to say, okay? So it's the moment of inertia about the centroidal axis, about the x-axis that passes through the centroid. That's the definition of this one. Over here, right, dy is a constant value. It comes outside of my integral. I'm just left with the integral of dA, which is just A, or the area. So I have the area times that parallel distance dy squared. Okay, this is my parallel axis theorem, and this is how I can find the moments of inertia about some axis other than the centroidal axis. I look up the centroidal axis in the back of the book, and I add that area times the distance away the reference axis that I'm looking at to the centroidal axis. Okay, so the procedure of this, again, divide your area up into simpler shapes. Okay, and then you want to calculate the moment of inertia about the reference axis for each of these shapes using the parallel axis theorem if needed. You know, if the reference axis actually passes through the centroid of one of your simple shapes, then you don't need to worry about the parallel axis theorem. But generally, you're going to need the parallel axis theorem to find the moment of inertia about that reference axis based on the centroidal reference axis that you have. Okay. Once you've calculated the moment of inertia for each shape, you simply sum them up to find the total moment of inertia about your reference axis. Okay. Of course, if any hole, right, if you have a circle with a hole in it, you would actually subtract off that moment of inertia to figure out the moment of inertia about the reference axis.